Hello, I'm Bernhard Stankewitz, and I'm presenting a joint work with Nicole Mücke and Lorenzo Rosasco, in which we provide a new recipe for deriving bounds on the axis risk of gradient descent algorithms for convex losses. In this short video, I want to give an overview of the core ideas of our paper and hopefully pique your interest to have a look at the preprint, which is available on arXiv. In the beginning, I want to give a short introduction to our setting. We consider n IID observations of an independent variable x taken from a real Hilbert space and a dependent variable y taken from a subset of the reals. Additionally, we assume that the independent variable is bounded almost surely in Hilbert norm. We then want to learn a linear relationship between x and y expressed as an element of the Hilbert space itself. We suffer the loss small l, of which we assume that it is convex, Lipschitz continuous with constant L, and also that it has Lipschitz gradients with constant m. This is an additional smoothness assumption. This setting is quite general, and in particular it includes the setting of classical kernel learning. The goal is then, of course, to minimize the population risk, capital L, which is just the expectation of the loss. Here we assume that a minimizer of the population risk, W star, exists in the Hilbert space, and therefore it is equivalent to consider minimizing the excess risk, which is just the difference between the population risk and the minimal population risk at W star. As an algorithm, we analyze gradient descent with non-decaying constant step size gamma, and a gradient update performed based on the gradients of the empirical risk, capital L hat, which is of course just the average loss taken over all the observations. As a final estimate, we fix a large iteration number t and average up all the gradient iterates up to then. And this average gradient iteration constitutes the final estimator. This is also quite common in the literature. For our analysis, we take the perspective of inexact optimization. That is, we regard our algorithm as performing gradient updates based on the population gradients itself, however distorted by a gradient noise term ET. For us, this is of course just the difference between the empirical gradients and the population gradients. Inspired by the literature on inexact optimization, we are then able to derive a decomposition of the population excess risk. On detail, we can derive that under our assumptions and the choice of our step size that is not too large, the excess risk at the averaged gradient descent iterate can be split up into a deterministic bias term here, which behaves as the inverse of gamma times t, which is the sum of all step sizes. And also a stochastic error part here, which averages up the dot products of gradient noise terms and the difference between the gradient iterates and the minimizer. At this point, it should be reiterated that these kind of decompositions are very common in the literature. Just to name a few examples, Betsikas and Tsitsiklis, Schmidt, Roux and Bach, and also in Young and Wei and Wainwright, decompositions like that appear. Going one step further, this decomposition reveals the two problems that have to be solved to obtain a rate result for the excess risk. Just by applying Cauchy-Schwarz inequality to the dot product here, we see that on the one hand, we have to control the gradient noise terms over the iterations, which is quite intuitive. And on the other hand, which is maybe a little more subtle, we also have to control how far the gradient iterates can in fact travel away from the minimizer. Both of these tasks will become more difficult the larger we choose gamma times t. So in fact, gamma times t can be regarded as an implicit regularization parameter for our problem. Structurally, this leaves us with the following. We have started with the idea of inexact optimization here, which brought us to a decomposition of the excess risk. And here we immediately see that the two problems we have to solve is on the one hand control of the gradient noise terms, and on the other hand, controlling how far the gradient iterates may travel. So we also have to control the gradient path. Fortunately, the gradient concentration arguments developed by Foster and co-authors in 2018 allow us to control the gradient noise and the gradient path both at the same time. In fact, based on their arguments, we can derive that under our assumption for a fixed radius r with high probability in delta, we have a uniform bound over gradient noise terms up to radius r in terms of an empirical Rademacher complexity, which can be treated as essentially 1 over square root n by a vector contraction inequality from Maurer, and two terms which are at most of the size square root log of inverse probability over n. Inductively, we can then, in high probability, with high probability in delta, bound the path of the gradient iteration by the fixed radius r, as long as the sum of the step sizes is not too large, and at the same time control uniformly all gradient noise terms up to the fixed iteration capital T. The fact that gradient concentration allows to control the gradient noise and the gradient path at the same time makes our analysis attractive compared to other approaches that have been proposed. For example, if we apply concentration of measure arguments directly to the population risk, as done for example in Lai Hu and Tang, there have to be extra arguments to control the gradient path, which can become quite technically and involved. Compared here, the gradient path is basically a corollary from the gradient concentration. In other approaches, this problem is avoided entirely by assuming that we have a known bounded domain on which we want to optimize the population risk, and this leads to projected gradient approaches. This is an additional heavy assumption, so it is nice that this problem can be treated by gradient concentration itself. Based on these structural results, we can now derive the main result of our paper, taking everything together. And this I want to now state in full. So under our assumption, with a choice of the step size which is not too large, we can, if we have sufficient control over the sum of the step sizes, which here we have formulated as a condition on the sample size, then we have a bound on the excess risk in terms of the bias, which we already discussed, and a stochastic error, which is of size square root log of inverse probability over n. And we also have a particular choice of gamma times t here, which allows to guarantee a bound of this size for the whole excess risk. And in this general setting, this is in fact the fastest rate known in the literature. Finally, let me give you a short overview of the references that I mentioned in case you want to look up any of those. And here, most importantly, of course, is the preprint that we have put on arXiv. So please have a look at that. And with this, thank you for your attention, and I hope you enjoy the German Probability and Statistics Days 2021.